All right, it's time, so let's continue. Bifurcation. Okay, so basically last time we talked about you have some baseline for some given function. Okay, then you have some kind of baseline for a fixed mu equals something, and then your baseline is going to change as mu changes. Okay, then a bifurcation occur if after you change mu to a certain threshold, the whole behavior, the long-term behavior of the whole function start to change. It's bifurcation, where the long-term behavior of the solution changes. For now, when we say long-term behavior, we particularly mean the number of equilibriums change from no equilibrium to 2, or the type of equilibriums changes. Something changed from a sink to a source, and something changed from a source to a sink or node. That's what we mean by a bifurcation happens. All right, with that in mind, what we can do is we can do something called a bifurcation diagram. That's actually 2. Okay, we did example. Basically, it's something like that. For the different parameters, you show me how the number of equilibriums changes by drawing a continuous changing of your long-term behavior. All right. So far, by looking at this, you can clearly see originally there was 2 equilibriums. After a certain threshold, there is 1. And then right after that, you have no equilibriums. So 2 to 1. And therefore to none. Then this is where the bifurcation happens. Okay. And particularly, this happens for the number of equilibrium changes. Okay. All right. Then for the second part, we want to study the second type of change. That is, even if the number of equilibrium doesn't change, the type change. Okay. When they say type, it basically means a sink become a source, or maybe the source become a sink. Good news is by linearization, we know a sink basically means f prime y less than 0. A source basically means f prime y bigger than 0. So if something changed from a negative to positive or positive to negative, that means the change happens when f prime y equals 0. It may not change, but if the change happens, it has to be here. Okay? So for type change, we look for 2 conditions. Number 1, f prime y equals 0. That's where it changes. And number 2, of course, it has to be equilibrium at first. So you need to add this condition. Sounds good? That's where we were left. Okay. Now I think this is pretty straightforward. We just need to show you an example, and that's all. So let's try this example. Y prime, y, 1 minus y square. Okay. Plus a mu. Your job is try to find the change, or just say where the bifurcation occurs. Okay. Well, two conditions. Number one, the number can changes. So we need to look at this one and see as we change mu, how will the whole thing change? Well, it's not hard to draw the graph. You can use Desmos or anything. The graph roughly looks like this way. Still okay? Now for some mu, you can see if the graph look like this way, by adding a mu, you basically shift this one up and down for different values of mu. Still okay? Cool. Then it really depends on how big mu is. If everything is like that, what do we conclude? One equilibrium, because we only have one intersection with the x-axis. The equilibrium is here. Good so far? For very big mu, this is what happens. For very small. Okay. Now this one can move up and down. For this case, can you see that you also only will have one equilibrium, which is here? Still okay? Cool. So where do you have something more complicated? That must happen when things are in between of these two. That means starting from here, I have three equilibriums instead of one. Still okay? Cool. So this is what I'm going to have. Let me draw all of them. For small mu, which means negative mu, this is the case. One equilibrium. Okay. For intermediate mu, it's like that. Three equilibriums. Okay. For large mu, which means you shift everything up to the extreme, it's going to be one equilibrium again. Sounds good? So where do you think the bifurcation happened? It happened twice. The first time is from one equilibrium to three equilibrium. The second time is from three back to one again. Okay, so the first bifurcation. It must be you're shifting this thing up to a point such that this one happened to be like this. A little bit below one equilibrium, a little bit above three. Okay, so what happens to this one? That's exactly when this one equal to 0 and this f prime y equals 0. Good so far? Okay, second, you have a second bifurcation if you keep moving up. That happens when this happens. A little bit below three equilibrium, a little bit above only one equilibriums. Sounds good? Okay. So finally, our job is try to figure out where are exactly the mu value. Then it's not hard to see. We just set f prime y equals 0 and fy equals 0 at the same time to find both. This means okay. From the first one, we know Good news is we do have 2. Now we know these 2. We want this to be true at the same time. We need to plug it back in. Sounds good? Then we can go back and put it in the graph. We have 2 bifurcation. This corresponds to mu equals -4/27, and this corresponds to mu equals 0. The bigger one should be the one which is above. That's where the bifurcation happened. Sounds good? Cool. It's not required because in general it's hard. However, for this one, you can actually draw the bifurcation diagram. So let's just draw it for fun. Different mu. Okay, a bigger mu only shifted the whole thing up. Therefore, the graph should look like, let me see, how do I want to draw this? Let me just draw this. Like that. Now we know this happens for mu equals -7/27. This is the second bifurcation at mu equals 0. I will just skip that. You can do it yourself to put all the arrows. Okay, that should be there. And down, that should be this, this, this. Actually, I need one more. Where is this? Okay, to make it like this, so we can show one more. Mu equals this, mu equals 0. Now up, down, up, down, up, down, down. All right. Okay. You can spend some time after class to draw all this. The key, however, is as mu changes, the behavior of your equilibrium changes. Okay. The 2 essential part, which is where the bifurcation happens, are what we computed by setting the derivative to be 0 and then find mu. Okay. Before that, 1 equilibrium, after that 3, and then after that another 1. All right. That's all we need. In general, now you know. If you have something like that, really, what's the phase line? Okay. What's the bifurcation? It all depends on this function here. Okay. It's a lot of information here. Now let's talk about the application. Right away, it's actually in your writing project too. Remember, you have something like this. Minus ht, actually. We call this one the harvest, which will change the behavior of the whole differential equation. Still okay? Now, let's make assumption in your step 2. Let's assume this one is a constant. Capital H. Then the whole thing become f y, which is dependent on the parameter h. Still okay? Then how many equilibriums do you have? Is it a sink? Is it a source? It really depends on what the value of h is. And the bifurcation can happen. Okay, that's basically what the question 2 is asking. What's the biggest value of h to still maintain the original sink and source? If you are bigger than that, you change the whole behavior. All right. Now to make it consistent with the book, we talk about the general format, but it's roughly the same. I think the book used the P, so let's just use P. Okay. We use k equals 0.2 in the writing product. We just take a k2 here and n here. And then the book uses minus c, but this is basically your h. Just f, c, y. Okay. This looks fancy. Now take a closer look. This is basically kp, 1 minus p over n. Okay, plus a constant. Still okay? Now if you focus on the first part, what is this? This is nothing but something look like 1 p times 1 minus p. If k is positive, this is the quadratic parabola. All right, so the shape look like this. Now by changing the value of c, you basically move this one up or down. Still okay here? Then think about what's going to happen. This is the minus. Basically, as you change the number of c, at the first we have 2 equilibriums. You keep increasing c, which means minus c, which means this one keeps going down. Still okay? For big enough c, what's going to happen? They are going to be tangent to each other. And you take anything a little bit bigger than that, it becomes this, and there's no more equilibrium. Sounds good? Okay, so that's what's going on with the bifurcation. Then we know when this is going to happen by drawing the bifurcation diagram. Diagram. All right, I will skip it. You can do it, very easy. We're going to have a sink and a source. After that, you can actually do it. It's going to be like this all the time. What do you mean by that? That means this. For no harvest, we have two equilibriums. The growth should be like that. This is no harvest. Still okay? Now, if you increase C, what's going to happen is you still have two equilibriums. But this time, these two equilibriums are closer to each other. Still okay? And then your final population is going to be smaller than before. That makes sense because you harvest something. Of course, the total population originally can stay at 5,000. Now you can only do 4,000. But somehow, it's still sustainable. Still okay here? Okay. Now let's take a big C. C is really big. C is bigger than the threshold. What's going to happen? No equilibrium anymore. What's going to happen is you're going to receive something, just keep going down. The population dies out. Why? Because bifurcation happened. Now you fundamentally changed what happens in the nature. Sounds good? Okay. So this one tells you, if you go there, you fish this much. You just reduce the final population for a little. You fish this much, you just reduce the final population by even more. But if you fish maybe this much, you break the whole thing and you won't have a final population anymore. All the fishes dies out. Okay? So bad, but still safe. Worse, but still safer. Still safe. And then even worse, and then it's not safe anymore. The population dies out. That's why we want to study where the bifurcation occur. And you better keep your harvest below that. Sounds good? Cool. Now, where does the bifurcation occur? That's easy. We just did it. We just need f prime y to be 0. And fy to be 0 to figure out what this number is. Okay. No, old trick. Fy is ky 1 minus y over n plus a c. F prime y is going to be k. Plus ky minus y over n. Okay. Set it to be 0. K minus ky over n plus minus ky over n. Y derivative, yeah. All right. Plus ky derivative of this. Okay. Okay. K minus 2k over n y equals n over 2. That is what makes f prime y equals 0. Now plug it back into fy equal to 0. You have c equals k n over 2 1/2 minus 1, which is negative k n over 4. Somehow something is wrong. What is wrong? The reason is because this was original minus. Now you have something positive. Yeah. Sounds good. So Andrew, yesterday you mentioned you Google online, you find the maximum constant, right? Now you can see actually we can get that thing ourselves. It's basically you find where the bifurcation happens. So totally makes sense. Well, what's the deal? It basically tells you if n is big, harvest more. That means you have a better environment. You have a lake, a big lake compared to a small lake. You have a rich lake with rich food compared to a small lake. Okay, that's good. Or if k is big, harvest more. That means you have a fish which can breed really quickly. The population grow really fast. Then feel free to go for it. Okay, makes sense. Second, this becomes interesting. This will be the final population if you just fish on the threshold. Still okay? That thing is regardless of k. That means this one only has something to do with the maximum capacity. Okay, so as long as you just keep fishing without breaking it, eventually it actually will be able to sustain half the population of the maximum capacity, regardless of k. That is long-term behavior, of course. Okay, so that's some interesting observations we have. Does everything make sense so far? Okay, so bifurcation and what's the application, right? We do the harvest. Now think about designing a parachute when people are trying to jump. I don't remember the formula, roughly something like, I better write it down. mv prime equals mg. Okay, that's the skydiving. Okay. Now maybe you can change the material of the parachute or maybe the shape, and eventually you may be able to change the bifurcation of the whole system to decide if this guy die or live. Okay. Another thing you can think about is actually, doing pharmaceutical things. That is when you have cancer, basically your cell grow exponentially. Still okay? It's a differential equation. Now what you do is you add some drug into it. What's going to happen is that thing is going to change the growth rate, and of course you want to reduce it. But still, it's going to be exponential. Still okay? Isn't that beautiful if you can add some kind of medicine and finally make bifurcation happen and change the whole curve to behave fundamentally different like this now? Or maybe even this. Make sense here? Okay, so that's actually how this one, why this one is meaningful in real life. It's actually everywhere in application. Okay. Any question before we move on to the next section. By the way, thinking about how to design an airplane, how do you know that eventually this one is going to take off if it just run fast enough? That's a bifurcation too. If you think about it, okay? So there's a lot of fun things to think about. But let's move to the next one. 1.8 linear equations. Very important. We talk about linear equations here. Later, we talk about linear system. Okay. For now, linear equation, first order, refer to something like this. This is linear. Okay. But clearly, everything I took in the red box is not linear. Right? You have sine, a t-square, and everything in there. So the key here is it's linear with respect to y. T can be anything. Okay. So this is good. This is certainly not good because now you are not linear with respect to y. Second, additional terminologies. We talk about homogeneous linear and the non-homogeneous linear. The difference is, does BT equal 0? Homogeneous? Not homogeneous. Because of this term here. Sounds good? All right. Why do we want to differentiate them into homogeneous and non-homogeneous? That's probably the question here. Is this the first time you see these terms? When did you see this one? Which class?
Linear algebra.
For what? Homogeneous and non-homogeneous. Do you recall in linear algebra something like that? Cool. Why? Well, think about it. When we introduce this one in linear algebra, what we were really trying to do is we were trying to do this. We say, hey, we want to solve this. Okay. How do you solve this? Well, number one, you solve this one for some x. Let's call it xp, x non-homogeneous, xn. You solve this when you have x homogeneous. Still okay? And then the solution of this one can be written as x, a special solution n, plus xh. Okay? Make sense so far? Okay, that's what we're trying to do. For example, if you solve something, you basically solve something is like 1, 2, 3 plus C1, 1, 0, 1 plus C2, 2, 4, 5. Do you remember? Your solution generally looks like this. You got one solution, which is a special solution, and you got the whole bunch of things here. All these things come from the homogeneous case. Or if you remember, it's called the kernel space. Or we call it the null space. Okay, that is what happens for homogeneous. And this is what happens for the non-homogeneous. And then you put them together, that's all the possible solution. Still okay? Why is it that case? Well, let's go even further. We do know this is happening because this one is how we found xn. We do know axh equals 0. That's what we mean by solution to homogeneous. But then we know a xn plus xh equals a xn plus a xh, which equals axn, which equals b. And this part goes to 0 because it's the solution of the homogeneous. Of course it's 0. Sounds good? The reason you decompose them into two parts is this part you add it or you don't add it, it doesn't change the value of ax. Because basically you're just adding 0 once you apply a. Make sense here? Okay, so that's why we have two parts. The part is one special solution. The other part is all the ones which produce 0. So you add them, you don't add them, you still get the same number. Okay, so if one thing is a solution, the solution plus whatever thing you put here is still a solution. Why? Because once you apply a, it's gone. Sounds good? We're going to apply exactly the same principle here for our differential equation. It's the same thing. So next time, if you want to solve this, how do you do that? Well, number one, I found one solution. Let's see the notes from the book. They call it, I don't know why they call it YP. For this. Then you found another solution for the homogeneous case, which is YH. Together, the general solution, Y, takes the format of the sum of these two. Because adding this or without adding this, you still got the same differential equation. Okay, that's number one. That's what we're trying to do. Sounds good? Second, then how do you actually make sure that adding this or without adding this, your solution stay the same? The essential step is actually here. That means when you have something, you should be able to split it into this, the first one, and the second one. This property is essential. Still okay? If you can't split things in this way, all the analysis I just did does not work. Okay. Do you recall how we call this property? We're basically saying fx plus y equals fx plus fy. That's called a linearity. That means your function is linear. Now, all the pieces are here. That's why we're talking about linear differential equations here, because if you are not linear, all the analysis I just did does not work. You have to be linear. Sounds good? Some quick examples to give you some idea. If you know f prime equals x squared, 2x, how do I solve that? Well, number one, I know f equal to 2x. F equals x squared. That's almost like my YP, a special solution. Good so far. Second, I do the homogeneous case. I set this one to be 0. I found f equals a constant. That's my homogeneous solution. H. Sorry. Good so far. What's my general solution? That's going to be the special one I just find, plus all the ones which satisfy this homogeneous case. That will be all the possible solutions. Make sense here? Okay. Why is this one good? That is because number one, this one prime equals 0. So add this one or without adding this one, you got exactly the same output of my function prime. Second, this one literally is linear. That's why we can do this. Okay. Yeah, all right. All being said, now we can just write down whatever in the book. The ideas is already here. Linearity principle. Okay. Number one, we have the homogeneous. Number two, we have the non-homogeneous. Okay. Now we solve the first one. We have a solution YH. We solve the second one. We have a solution YP. Then the general solution of 2 is given by y equals YH plus YP. Sounds good? That's the principle. This is the first part I really hate this book. They did everything here very formally, but actually this one works for any order of differential equations, not just first order. For example, how are you supposed to solve this? Think about it. Number one, this come from a spring mass system. Okay. And it is linear. As long as it's linear, it really doesn't matter which order do you have. You can have third order, fourth order. You basically just solve two things. Number one, you solve this one for one solution. And then you solve this homogeneous one. Oh, y plus 13 with another solution. Okay. Then your final solution is going to be YH plus YP. Still okay here? Cool. Now I'm going to write down the solution. It's actually not too surprised. Where this part is the solution of the homogeneous, and this part is just one special solution. Make sense so far? Okay. You can solve this yourself. It's pretty easy. But the key here becomes really interesting. What is this? This is a linear combination. Actually, all possible linear combinations. Of sine k over mt and cosine square root of k over mt. Your C, C2, C1, C2 can be anything, right? Okay. That have several implications. Number one, these two are linearly independent. Otherwise, I don't need two, I just need one. The other one is the multiple of this one, or linear combination of this one. Second, if I write everything this way, this gives you something which is called a two-dimensional solution set. From here, you can see this is actually a vector space or a subspace, depending on how you want to call it. Okay, and it can be written as span Now I think you can associate that thing to the kernel space. Or some people call the null space of A as a matrix. But of course, this time we don't have a matrix anymore. We have a linear operator. Sounds good? Okay, we're not going to touch the details here, unfortunately, and this book won't touch this one anymore in the whole book. That's one thing I'm really not happy with this book. Okay, so I just want to show you this idea here. This is probably one of the most important ideas, but this book doesn't have it. Now let me write down something random. What's the solution of this? Sounds good? Okay. This is what I'm going to do. I'm going to find one solution. Use whatever technique I find, a special one. I'm going to plot the solution of the homogeneous case. Still okay? Number 3, by looking at this, I know this one is going to be 3-dimensional. Because if it's linear, every order give you one more dimension. Still okay? So from the beginning, I know this one is going to be C1 something plus C2 something plus C3 plus something because of this number here. Still okay? Now, all you need to do is just go inside and find 3 linearly independent solutions. Once you find 3, and you know they are linearly independent, you can stop. Why? Because you're looking for something 3-dimensional, and you have just found a basis for that space. You don't need 4, you don't need 5, you don't need 6. Does that make sense to everybody? That's the beauty of this theory. That basically tells you when you can stop looking for more solutions. Okay, once you found 3 linearly independent ones, you know you can stop. Because why? Because even if you found another one, that one is definitely guaranteed to be a linear combination of the existing ones. So you can stop here. That's why I say this is probably the most important ideas. Okay. I know it's kind of vague. I didn't give you this examples. Okay. But that's the idea I'm trying to deliver. And we're only going to touch it here. We don't have rooms later to touch this one. And basically 1.8 is over. Any questions regarding what we have here? Okay, just a quick catch up. I know I said a lot, which is not too solid, but the key is, number 1, look for something called linear. Once you have something linear, you know your solution looks like this. Okay. This part, you always have one answer. This part, you have infinite many answers. But they will be in a form of a linear combination of only a few functions, which come from the null space. Okay. Linear combination of the homogeneous equation of the solutions. That's the key. Okay. That's all for today. I can stay for another 10 minutes for questions, so feel free to stay.